All right, fourth time's the charm. I've recorded this video 4 times now. I published the third one, but honestly, I wasn't happy with it. I want to do this one last time. So I broke up the examples again. This is continuing from the last video, solving systems of equations with 3 unknowns. That's the topic of this video. So I've got 3 examples here for you. Example 4, example 5, example 6. Ooh, I want to erase all that. Let's make that boop, 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 boop. Just get rid of that. That was from the last video. We'll be fine. Okay. So before I start solving any of these, all 3 of these have something in common, and that is because they are 3 equations and 3 unknowns. I'm just quickly scratching that out. They're 3 equations, 3 unknowns. So I'm going to have x, y, z to solve for, and I'm going to have 3 equations with that. Now, it doesn't necessarily mean each equation has all 3 unknowns, right? If you take a look at, where's my laser pointer? Right here. This fella right here, second equation in the middle, there's no x terms, right? So, it's not going to have all 3 in each equation, but the idea is that we are solving for 3 unknowns. So, general strategy, and this is before I write anything. The general strategy for solving a 3x3 is to use elimination procedures to reduce this 3x3 system to a 2x2 system. Now, the 2x2 system is what we covered in the previous video, and if you've taken Algebra 1, which, how could you be in Algebra 2 if you weren't in 1, right? That's what you solve in Algebra 1, is 2x2 systems. That is when you have 2 variables and 2 equations to solve. And like I said, last video, so if you apply that logic, 2x2 systems aren't so bad. But 3x3 can get messy, and you got to be careful. There's a lot of ways we can go about doing this, but I'll give you a sort of general strategy here. And the general strategy is to first align your variables. You don't have to do this, especially not if you choose a substitution route, right? If you choose a substitution route, you'll want to solve for a single variable, take that expression, plug it in somewhere else. But if our goal is to reduce this system to a 2x2, usually elimination is going to be the better approach. But hey, this is a case-by-case basis, and who knows what your brain notices. You might see something brilliant that's actually more efficient to use substitution rather than elimination. So if you see that, you're welcome to do that. All right, I'm saying all this to convey the idea that you have a lot of choice here. It's up to you to decide what you want to do, whether you want to use a combination of substitution or elimination to reduce these 3x3 systems to 2x2 systems. I'm going to show you how to do this, all right? Okay, let's get started. So the first thing I recommend, step 1, is to realign your system. So I'm going to use blue here. I'm going to do a little double arrow like this. And all I'm going to do is rewrite the system so that it has each x, y, and z term on the left side of the equation and the constant term on the right side of the equation. So in essence, I'm making an x column, a y column, a z column, and then there's going to be an equal sign everywhere, right? And then I'm going to have my constants in their own column, like so. 2 reasons why I'm going to do it this way. Number 1, aligning your variables helps you keep track of elimination procedures more easily. Makes it clear to your reader and to yourself what you're eliminating, and prevents any, just mistakes in general. For instance, if I had 3x plus 2z, and I had negative 3y plus 8z, right? Well, if you added these together, sometimes you might say, oh, 3 and negative 3, that cancels. So it's just 10z, right? And that's because your brain's looking at the vertical alignment of this without really noticing what the variable is. So if you kind of get rid of that, if you just align them in the first place, you'll avoid silly mistakes like that. Okay, but that's just a sort of recommendation for elimination. The second purpose behind this is in lesson 3.2, we're going to talk about Gaussian elimination, which uses matrices. And when we work with matrices, we're going to end up aligning these variables in this exact form anyway. So it's probably a good practice to start doing it now. All right? Okay, so I've explained why we want to align them. All right, let's do it. So the top equation, I've got 3x minus y. Notice I'm talking about this guy. 3x minus y equals negative z. I am going to add z to both sides to take this negative z and move it to the left side of the equation. So let's do that. 3x minus y. I'm going to now add z so that this equals 0, right? Because notice, of course, negative z plus z equals 0. I really like this laser pointer. That's so cool. Let's say hello. Look at that. Oh, that's so cool. I love that. All right, sorry. I'm just geeking out over this technology. Okay, now I've got y plus 2z beneath. Now, I want to align this, so I'm going to just put the y's underneath each other, like so. And then I've got the last equation, x minus 3z equals negative 5. I'm going to align this as well and put the x here minus 3z here. And this equals negative 5. All right? Look, you don't have to do this, but I recommend it because seeing this alignment, I think you're going to notice more patterns. All right? You're going to notice more patterns. And in fact, perhaps you're already noticing something extraordinary. It's funny, I created this example just off the top of my head, and yet it is a unique example where we get to eliminate two variables in one smooth motion. I want you to observe this system of equations here and think, our goal is to eliminate variables, right? We're trying to reduce this system to be smaller, right? We have 3 unknowns. We want to reduce it to 2 unknowns. We'll take 2 unknowns and eliminate it to 1 unknown, right? And then we'll solve for that 1 unknown. But notice we actually get pretty lucky here. Negative y and positive y will cancel out when I add them. Those are additive inverses. And simultaneously, if you were to add all 3, positive z plus 2z minus 3z. Hey, z plus 2z minus 3z equals 0. Isn't that cool, right? So if I were to add all these together, 3x plus x is 4x. I get negative y plus y is gone. And then z plus 2z minus 3z is also gone. And this equals 9 plus negative 5, which is 4. So therefore, x equals 1. Right? Because 4x equals 4, right? So I don't know if I want to write that. That might confuse you guys. 4x equals 4 implies that x equals 1. How's that? Is that a little bit more clear? All right. Equals 1. Nice. Cool. So now what? Right? Now what do I do? Well, I've got a result for x. I found x equals 1. I can now use this and use substitution to find y and z. So the only question is, where do I put this 1? Right? I've got x equals 1. Where do I put this? Well, I could put it in the top equation here. Take a look at that. 3x minus y equals negative z. If I do that, yeah, it substitutes x away, but I'll still have y and z, which are 2 unknowns. So that doesn't really help me. If I use equation 2, I don't actually have an x to substitute, so that's not very useful. So I'll move on to equation 3. So that's what we'll do. I guess we will just say boop. We'll move on to equation 3 and say, hey, this is x minus 3z. X minus 3z equals Was that negative 5? Okay. Negative 5. Sorry, I'm jumping all around the place. And I said x equals 1. So substitute x equals 1. 1 minus 3z equals negative 5. Subtract 1 from both sides. Negative 3z equals negative 6. Divide both sides by negative 3. Z equals positive 2. Cool. Awesome. So far so good, right? I found x, I found z. And now I have a couple options. My options have opened up. I found x, I found z. I could substitute x and z into the first equation because x and z are now known, making y the only unknown. The other option is to substitute z into the second equation. Then I don't have to do as much math with x, so that's what I'm going to do. But both methods will solve for y. So I'll say equation 2 is y plus 2z equals 9. So we'll replace z with 2, like so. You see how I substituted that? Y plus 4 equals 9, so y equals 5. Okay? And when you're showing work for our exams, please make this very clear. Okay, please make it very clear that you substituted 2 in for z. If you go from this step and just jump and just say y equals 5 after, you're doing a little bit too much mental math, all right? I would like to see that you've identified which equation you're going to substitute z in and show that substitution. Now, if from this step you can deduce that y equals 5, hey, that's fair game, that's whatever. But please make it clear, not just to me, but your reader, right? Whoever's viewing your work, it needs to be clear what you're doing. You might say, why does this matter, Mr. Spake? You know what I'm thinking. Well, maybe I do, maybe I don't. But if you're going to be in AP Calculus, if you're going to take BC Calc or AB Calc, there are free response questions where showing your work is of utmost importance. And if you don't show your work on those, you're not going to get enough credit. And they can make or break your college exam score. It's the difference between a 4 and a 5. If you know what those are. If you're even in an AP class right now, maybe you are, maybe not. But just something to keep in mind, all right? Plus, it's just good general practice. I mean, come on. Okay, so I found x, I found y, I found z. The way I'm going to write this final answer is as an ordered triplet. So I'm going to say this is an ordered triplet. X, comma, y, comma, z. This is for three-dimensional space, right? X and y is 2D, so x, y, z is 3D. If you've ever seen a 3D diagram, right? If this is my x and y plane, sorry, this is terrible. I'm so sorry. This is the worst picture ever. There's my x and y plane. The z plane goes that way. If you can kind of interpret this coordinate system, giving that depth, yeah, kind of, you're going to deal with a lot of three-dimensional stuff in calculus, at least in BC Calc you will. Okay, so x, y, z, x is, I believe we said 1. Was that true? Okay, 1, y was 5, and z was 2. I know. You say, Mr. Spake, why do you talk about calculus so much? Because I love calculus. It's so cool. Look, I know that a lot of what we do in here so far, maybe as you're learning, as you're experiencing, seems like busy work. And truth be told, it kind of is. But, man, when you get to pre-cal and calculus, especially calculus, it all makes it worth it. I mean, it really is just so worth it, seeing what all this stuff is good and useful for. It's kind of like, before I move to example 5, it's kind of like if you showed somebody a box of tools and he said, well, that's great. It was wonderful seeing a hammer and an axe and all these kinds of, an axe, maybe an axe isn't a toolbox, but you know what I'm talking about, right? Nuts and bolts. But you really marvel at the house that was created, right? Algebra is the hammer. What I'm going to do, the hammer. That is my best hammer. Algebra is the hammer, but the house is calculus. And that's what we're all going for, right? At least that's what kind of we're hoping for. Okay, so let's move on to example 5. In this example, we're not so lucky. Notice in the previous example, we got lucky because once I aligned my variables, 2 variables were eliminated by adding all 3 equations, and I didn't even have to alter them. They just lined up that way, which was really nice. This example, however, is going to be a little bit more complicated. So let's take the same approach of aligning our variables. So I'll do a little arrow here. I'm going to make a little curly bracket. I could never do a perfect curly bracket. I always do some. So x minus 4y plus z equals 1. I'm just copying that down. But this next equation, this guy, I want to add z over 2 to the other side, right? See, that's negative z over 2, so I'm going to add z over 2. That way that cancels and moves this guy here. Okay, so I'm going to say, I'll put my 3y underneath here, and then plus z over 2 equals 0. And then the last one is take that minus 3x and move that over here by adding it. So I've got positive 3x plus 4z equals 6. And there you go. And just if you don't like this empty gaps, these empty spaces, you can fill these gaps with 0x and 0y if you'd like. All right, you can fill those gaps in because, really, there's just no x's there, there's no y's there, so this has a coefficient of 0. I'll leave it blank, but you're totally welcome to do that if you don't like that blank space. Now, shoot, right? Shoot. This fella is complicated, and nothing cancels, right? This is x and 3x do not eliminate. Negative 4 and negative 3 don't easily eliminate. And none of these eliminate, right? None of those z's. So remember what I said earlier. What's the goal? The goal is to eliminate a single variable and reduce this to a 2-by-2 system that is now easier to solve. So we must ponder. We must think. Let us reflect. I have 3 choices here. I could eliminate x, I could eliminate y, or I could eliminate z. Now, if I eliminate x, right, suppose I get x away. If I can do that somehow, I will have a system of y and z left over, which I could solve. If I eliminate y, I'll have a system of x and z that I could solve. And if I eliminate z, maybe I would have a system of x and y that I could solve. However, I don't actually think that happens in this problem. If you play around with the z, I think you can eventually get to just x and y, but it's going to be more work. Choose x or y. That's actually the better choice for this example, although your choice doesn't really matter a whole lot. I noticed that x and 3x are most easily created to be an additive inverse. With 4 and 3, I would have to multiply those by each other to get 12 so that they'll add. That's just more work. So what I'm going to do is take the first equation, x minus 4y plus z equals 1, and the third equation, 3x plus 4z equals 6, and I would like to eliminate x. So in order to do that, my goal is to make this x a negative 3x. That way this negative 3x cancels with that 3x. So I'm going to multiply by negative 3. So the top one is going to get multiplied by negative 3. Multiplied by negative 3. So let's do that. Negative 3x plus 12y minus 3z equals negative 3. Is that right? Yeah. Be really careful when doing your arithmetic. That can hurt a lot. That's the reason I've had to film this video 4 times, is because of stupid arithmetic. That and the last video was fine, but I yawned too much. I was just yawning the whole video. It was not good. It was not professional. Okay, so let's align this now. And we'll add, and negative 3x with x cancels, right? Those guys are eliminated, and I'm left with now 12y, is that plus z? Plus z, 1z, equals 3. Okay. We're in good shape here. And it may, you may say, well, Mr. Spake, what have we really accomplished here? You eliminated x, but you got 12y plus z. What good does that do? Uh-oh, I mentioned yawning, and now I'm having to yawn. This is not good. I hope I do not start yawning all video. That would be a bad omen. Okay, so this fella, 12y plus z equals 3. Notice I have y and z in this equation. At the same time, the middle equation, I have y and z. So I'm going to, let's align these. I'm going to take this equation and just put it down here so that it says 3y plus z over 2 equals 0. Now you can eliminate one of those variables, and it doesn't really matter what you choose. You could eliminate y, or you could eliminate z. It doesn't matter. Sorry. I told you. I said the word yawn, and now I'm going to start yawning. Isn't that how that? You're probably yawning right now. Just the word alone is contagious, isn't it? Okay, sorry. I'm getting off track here. Refocus, Mr. Spake. So I want to eliminate either y or z. I have the choice here. I'll choose to eliminate y. If I multiply the bottom equation by negative 4, here's the result. The top equation stays 12y plus z equals 3, but the bottom equation becomes negative 12y minus 2z equals 0. Notice negative 4 times z over 2. That's negative 4 over 2. That's negative 2. Now I add these. These will cancel, and I will get negative z equals 3. Therefore, z equals negative 3. From here, I mean, once you solve one of them, oh, it's so nice. It's such a relief. Once you finally get one of them, finding the rest is not so bad. It's just the process of getting to that first one. Now that you found z, you can take z and substitute it somewhere else. So, I'll highlight, we have a few equations here. We have this equation, and we have this equation. Either or, I can substitute z into one of those. I also have this one, right? 12y plus z equals 3. Why don't I do that, right? Why don't I figure out what that is? So I'm going to do 12y plus z equals 3, but z is negative 3, so this is 12y minus 3 equals 3. Add 3 to both sides. I get 6. Divide both sides by 12, and y equals 6 over 12, which hopefully you recognize that means y is 1/2. Now, find x. That last equation, you could use all 3 on the top equation, or you could just do the last equation. 3x plus 4z equals 6. 3x plus 4z equals 6. So z is negative 3, so it's 3x plus 4 times negative 3 equals 6. So 3x minus 12 equals 6. So 3x equals, what is that, 18? So x equals 6. And there you go. my ordered triplet is 6, comma 1/2, comma -3. That's for x, y, z. And we are finished. Now, a word of checking. I'm going to show you, well, gosh darn it. Oh, I really screwed myself with that yawn comment, didn't I? I really, darn. I'm sorry you have to endure that now. I frantically apologize. To check your solution and make sure it's true, plug x, y, and z into all of them. It should check out for all three equations. If you get them all true, then you know your solution is true. So that's kind of like checking for extraneous, although you're not really getting extraneous solutions in this process. We don't really get extraneous when we solve linear equations. It's more complicated things that we get extraneous. But nevertheless, checking your solution is recommended. And now we're going to move on to example 6. But one last word about that is on day, I think 3 or day 4, I'm going to show you how to use the matrix calculator to check your answer. And you're going to love that day. You're going to love that day so much. So, and that's not even a sarcastic like, you're actually going to love that day. You're going to scream for joy. You're going to love it. Okay, example 6, and this is the big one. This is the big caboose, all right? This is the big boy. We need to solve this 3x3 system where every line of the equation has 3 variables. And so this can be a lot of work. Now, if you get good at this, you can do this real fast. But it takes a while to get good at, all right? I don't expect you guys to be lightning fast with these processes, not even by the end of the unit, okay? This is something you just build over time. First things first, let's align this. All right, let's align it. 4x minus 3y minus z equals -7. 5x plus 2y minus 2z equals 5. And x plus y plus z equals -2. If you don't know what I just did, pause the video and figure it out. I'm just aligning the variables, okay? All right, so here's my strategy. As I've said before, we want to use elimination to reduce this 3x3 system to a 2x2 system by eliminating the same variable in 2 pairs of the equations. So, strategy, pick a variable to eliminate. In this case, there's any suggestion goes. If you want to eliminate x, fantastic. If you want to eliminate y, phenomenal. If you want to eliminate z, way to go. I don't care. It doesn't matter. I'm going to choose z mainly because -z and +z are easy. I mean, those easily cancel out. I don't even have to do any arithmetic, at least not in terms of altering the equation. And then -2z, if I double this z and make this 2z, then those will cancel. So that's what I'm going to do. So I'm going to pick equations, I said 1 and 3. So equations 1 and 3 is what I'm going to pick. So I get 4x minus 3y minus z equals -7. I get x plus y plus z equals -2. I will add these to eliminate z. So you get 5x minus 2y equals -9. Okay, because z is eliminated. I'll do it now again with, what was my other choice? Equations 2 and 3. So I'll write equation 2. And beneath that, I'll write equation 3. Like so. But like I said, I want this -2z to eliminate with this z. So if I made this +2, then those will cancel out. So I'm going to double the bottom row. 2x plus 2y plus 2z And negative 2 doubled is 4. I'm going to add now. 5x plus 2x, 7x, then plus 4y. The z's are crossed out, and 5 minus 4 is 1. So look at what's happened. We went from a 3 by 3 system, and now what I've done is I've created one equation with two unknowns, a second equation with two unknowns. This is good. And they're the same unknowns, right? X and Y, X and Y. If I align these, 5x minus 2y equals negative 9, 7x plus 4y equals 1, I can now eliminate. Y looks like the better option here. If I double the top line, if I multiply the top line by 2, that's 10x minus 4y equals negative 18. Keep the bottom the same. And add, and I get 17x, the y's are canceled out, equals negative 17. Divide both sides by 17, and x equals negative 1. Hooray. Now, with this result, this x equals negative 1, you might be inclined to go back to the original and try to plug it in here. That will accomplish nothing. Notice if you plug in x here, here, or here, you still have y and z's that you don't know. So you can't plug it back up in the original, but you do have two different equations, both with one x and one y. So let's pick one. I'll pick the first one. 5x minus 2y equals negative 9, but now I'm going to replace x with negative 1. So this is 5 times negative 1 minus 2y equals negative 9. That's negative 5 minus 2y equals negative 9. Add that over. Am I doing this right? Did I do anything wrong? Sorry, I was just thinking. Negative 2y equals negative 4 by adding those 5s. So y equals 2. I think that's right. Yeah, that seems right. Y equals 2. So I've got y equals 2, x equals negative 1. Neither of these equations have z's, though, so I will have to go back to the beginning. I've got the first one, I've got the second one, and I've got the third one. The third one looks the easiest, right? X plus y plus z equals negative 2. So let's do that. X plus y plus z equals negative 2. X is negative 1. Y is 2. So negative 1 plus 2 is 1. 1 plus z is negative 2. Oops. Brain jumping ahead right there. Subtract 1 from both sides. And z equals negative 3 is your final answer. And we are done. My order triplet is x is negative 1, y is 2, and z is negative 3. Ta-da! We have finished. Oh, I feel so much better about this video. I feel like this was much better explained than the previous 3 attempts. And with less yawning. Albeit some yawning, but less yawning. So, there you go. I hope this was helpful in reviewing these systems. Yeah, look at all 3 of those. I know that I just threw these at you and said, go. I know that. And you might be complaining, Mr. Spake, you haven't taught me anything. Well, I did, right? I taught you some of these rules here to look out for, and I showed you nice 3 solid examples, right, to reference, and I challenged you to figure out the rest, right? That is going to happen in this class, just so you're aware, okay, that's going to happen. I'm not always going to show you how to do everything. Sometimes I am going to challenge you to figure it out for yourself. Because that is what builds us as true mathematicians. So yeah. Okay, well, thanks for being here. I hope you found this video helpful. I'll see you guys in video 3.2, where we get to talk about Gaussian elimination. See you then.